Dmitri from AT&T Research Labs, and he's going to talk about query reverse engineering.
So good afternoon, my name is Dmitri. So we're switching gears completely. We're considering completely different problem, which is a query reverse engineering. So this is joint work with Lux Lakshmanan of University of British Columbia and Devesh Srivastava. So let me first define the problem. So in the problem of query reverse engineering, you are given a table, route. So it can be some table in some database, or it can be in the form of an external file, such as an XLS file. And you know that there is a database, and this table was generated as a result of a query run on this database. However, the query is not known for whatever reason. Maybe the person who created this query left the company or is not available. So your task is to find a concise query QGen, such that if you apply this query QGen on the database, it generates the desired table route. And in this specific paper, we consider only project join SQL queries. So to place the QRE problem in the context of other important database problems, so if we take something like query processing and data provenance, so in terms of what is known and what is not known, so for query processing, obviously we know the input, we know the output, the query, but we don't know the output. So for data provenance, we can say that we know the output, we know the query, but we don't know the input. So for query reverse engineering, we know the input, we know the output, we need to figure out the query. So in terms of use cases, there is a direct use case for this problem, where the analyst, let's say, discovers some table, and this analyst would like to augment this table in some fashion, but the query is lost. So the analyst needs to find this query. But in my opinion, what is more important is that the technology used by, developed by QRE can be very useful for other problems, such as data integration, data provenance. Specifically, there is a variant of QRE that can address the following data integration challenge. Imagine the user specifies a scheme of a table and also provides a few result tuples, and then asks the system to basically generate the table that includes those tuples. For data provenance, what you can do, you can go over tables inside your database and try to discover data provenance by using QRE algorithms. And this will provide you very detailed information as to which columns, how columns were generated from which tables and which other columns. So the main challenge for QRE is efficiency. And to understand why this is the case, let us consider this high-level pseudocode for how many query reverse engineering algorithms work. So the way they work is that if we look at, let's say, the first line, first they do some kind of pre-processing, building indexes and so forth. So then there is a magic black box that generates a candidate queries. So then you have some kind of a filtering mechanism that tries to filter away wrong candidate queries. And then you have this test. When you take the candidate query, you apply it to the database and see if it results in a route or not. So having this pseudocode, what we can observe is that actually the search space is huge for this problem. So the specific variant we consider in this paper is NP-hard. But what is more important is that running this test, as you can imagine, can be very, very expensive. So if you have a large database and you need to run a query on it and then check if it's a route or not, this can take a lot of time. So this gives you the intuition as to how you can design an effective query reverse engineering algorithm. So the first thing that you need to do, you need to try to avoid executing this costly test as much as possible, because it can take forever. So essentially then what you can do, you can design a very effective ranking mechanisms to generate candidate queries in rank order. And this mechanism should be very good. It should try to guess queries, candidate queries well. And of course, the next step that you need to do, you need to design very powerful filtering techniques to filter away wrong candidate queries. So now this slide presents the architecture of our solution. So it consists, you can see that at high level, it follows the same paradigm explained like in the, on the previous slide. So it also has pre-processing, it has the candidate query generation module, and it has a query validation module. So, but it also consists of lots of different subcomponents to make the solution effective. So in this talk, I will just present intuition for two components, which are called direct column coherence and indirect column coherence. So to present those subcomponents, let us have a look at this toy database. So we have a table route. You can see just a small table that consists of basically 4 columns, and you have a small database consisting of just 3 tables. So it's you can check that a route can be derived out of those 3 tables by performing a simple join. So it's also outlined here, but the query is unknown to the query reverse engineering algorithm, so it needs to be discovered. So, and this join does this. So this is a simple join. So if you can imagine, maybe this is a primary key and this is a foreign key, you just do this join via A and D and A and F. All right. So before you start, you kind of let us understand how like query reverse engineering algorithm would work. So you need to, for each column in this table, you need to figure out which columns it could have been derived from. And initially when you start, you take something like column Z and you say, okay, it could have come from any of those columns before any analysis. So what pre-processing does, it says, let me actually analyze values in those columns. So for Z, you will see A1 and A2. Then you say, aha, A1 and A2 is only present in E. So the only column, so the cover for column Z is column E because like the values could have come only from this column in a project join query. So, and you can write this observation in this formula involving projections. So if you take a route projected on column Z, it should be a subset of R2 project on column E. So using the same logic, we can say, we can basically extend it and say, okay, for column Y, it could only be produced by column B, and for W, we see again B5, B3, they're only present here, so those values must have come from column G. So it's like right now, everything is nice, we don't see any ambiguity. However, we see a problem for column X. So using the same logic, now we see that actually 3 columns could have covers column X, so we need to pick one. So that's uncertainty number 1. So uncertainty number 2 here is that imagine somebody even tells you, no, it's not three options, it's only one. Somebody tells you basically the cover for X is C. So then we have a different type of uncertainty. We notice that columns B and C, they come from the same table R1. And then the question that we will have is that, do they come from the same instance of R1 or 2 distinct instances? So remember, queries might have different instances of the same table, right? Let me now present the first technique that is used in the paper. So it's called direct column coherence. To understand how it works, let's ask ourselves a question. So we have this table R out, and we look at columns X and Y. Is it possible that those columns have been generated from columns A and B from the same instance of R1? So at first glance, it might be possible because you have values like 1, 2, 3, 4. These also have 1, 2, 3, 4. But the answer is actually no. And the reason why is because column X and Y, they have a tuple 3, 4. And this tuple is not in columns A and B, so which is written in a similar fashion to pre-processing step. So you say RL project on XY is not contained in projection of R1 on AB. So it's not possible. Let us look at another example. So let's take table R1 and transform it slightly for convenience into, so we have ABC columns, so we will just write it ACB for convenience and say, okay, is it possible that columns XY have been derived from C and B using the same logic? And the answer will be maybe. And this is because tuple 3, 4 is covered in column CB, and tuple 1, 2 is also covered in column CB. So in such a case, we will say, so we can write again this as this equation, and we will say that columns C and B are coherent. And here we have a very important question. Let's imagine you have you have a large database, and you found that some columns in some tables are coherent with your ROUT table. So is this relationship just by chance, or is it telling us something? So this paper is based on the intuition is that it actually tells you more, so it's often not by chance. So instead it provides you, in this case, a hint that columns C and B have been used from the same instance in generating query. So let's see how we can use this hint. So remember we had uncertainty 1, where we said, okay, X could have come from 3 possibilities. We don't know which one. But hint tells us that C and B may be involved in QGen. So we might want to first try column C as cover for X, because if we don't do it, C will not be involved in QGen. So we just basically do exclusion. So next uncertainty that we had is that we had the question of whether C and B come from the same instance of R1 or from 2 distinct instances. And the answer to this question could be maybe you first need to try the case where they come from the same instance, because they look consistent. They look as if they came from the same instance. So this provides us a hint. So this logic amazingly can be basically enhanced even further. So now I will describe a technique which is called indirect column coherence. So far what what basically our technique tells us is that it looks like all 3 tables are involved in generating table ROUT. We just need to figure out how to basically join them. But before doing the complete join, we will do stuff incrementally. Specifically, we need to answer this specific question. So the join, again, just a reminder, it looks like this. So the question is, can just a partial join like this, R1 and R2, be a part of QGen, specifically such that columns XY are generated from column CB and column Z is generated, column E is generated, column Z is generated from column E. So, and we can extend this logic and say the following. So if the projection of ROUT on columns X, Y, Z is contained in the projection of R1 join R2 onto column CBE, then the answer is maybe. Otherwise, the answer is no. And this condition can be used as a very good filter. So, so far, I basically covered the first 3 pages of our paper. So I just presented basic intuition. Okay, and I covered only 2 techniques. So the paper obviously contains much more information. So it also covers different techniques, and it presents a principled approach that combines those techniques into a single solution. So now let me cover experiments. So this graph compares our technique to the state of the art. So this was published in this paper. So what it does specifically, it shows this speed up over the state of the art for the queries tested in this paper. And it only shows the bars for the cases where the improvement was at least 1 order of magnitude, because we thought, okay, if it's less than that, maybe the techniques will just declare them to be comparable. So, and you can see for lots of queries, we see a very good improvement of 1, 2, and even 3 orders of magnitude for query 5, we see 3 orders of magnitude of improvement. So the technique is quite powerful. To conclude, or the main takeaways is that by using this technique, you can get orders of magnitude of improvement. In our personal opinion, the most value of our work is actually in techniques. So don't treat this paper as a framework paper, but the techniques described in the paper, we believe, can be very useful for solving various problems. And those problems are not necessarily only query reverse engineering. So you can apply those techniques for certain cases for deriving data provenance and data integration. All right, thank you.
The evaluation was based on a real system, right? What database system did you use?
So the evaluation was based on SQLite.
Okay. And I'm wondering, not all queries, it seems that in your algorithm you showed in the very beginning, right? At no point did you consider query cost. So it might be that, like, you know, I can explore cheap queries much quicker than expensive queries, right?
I can explore cheap queries. Yeah, so for cheap queries, different techniques will perform roughly the same. So you see most of the difference for complex queries.
Okay. Well, and then maybe based on that is, like, you know, I mean, if you have these ideas of adaptive indexing, right, where like the system learns with one query, learns to accelerate the next. So I would wonder that, like, exploring points in a similar area would would be much cheaper than hopping through the query space all over the place, right? Do you have any, like, notion on that?
So there are lots of different optimizations. So the second filter I described, which is indirect filter, it tries to do like incremental query building. So if it sees a part of the query cannot be in a generating query, it kind of quits all possible candidate queries that include this kind of subquery in them.
I think what I'm driving towards mostly is, like, is there a value in cracking open the database? Basically taking into account how the system evaluates queries, query cost, indexing, all of that.
Yeah, that's a good question. So one of the, I will not answer it directly, I will answer it indirectly. So one of the techniques that the paper also uses a lot, and we actually don't the system uses, we don't maybe describe everything in our paper, is that we use query optimizer a lot to estimate the query running time. And this running time is used in a lot of kind of decisions. So we say if this decision is more costly than that decision, maybe we should not run it. Yeah, stuff like this. Mm-hmm.
So are you aware of another work, Query Reverse Engineering in VLDB 2015 by Tran and the authors? It's called Query Reverse Engineering, and they cover apparently select project join queries. Mm-hmm. The problem definition is same. So how do you contrast that work? Because they also consider selection beyond projection and join.
Yeah, I will need to have a look at it more closely because I just, I don't know all the details. Not off the top of my hand, yeah.
Okay, maybe you can look at that paper.
All right,
yeah.
okay.
Thank you.
This also answered my question. So my question was also on the scope of the queries that you support, that you can discover.
Mm-hmm. The space of queries?
Yes.
So this technique is only for project join queries. So we don't consider, so it doesn't consider any other queries.
Okay, cool. Let's say thanks last time. Thank you. Okay. So the fourth talk is adaptive energy control for in-memory data.